Good morning. We are going to start the remaining part of yesterday's theory, that is known as the band theory of metals, which is also referred as a molecular orbital theory, because most of the aspects of this theory that is based on the molecular orbital theory. Hence, the band theory of metals is also referred as the molecular orbital theory. To proceed further with the next part of this band theory, because yesterday we have finished only the introductory part of this band theory, actual part we are going to study today, for which we have to recall again some part that we have already covered yesterday, that is very much beneficial for the better understanding of this theory. As we know that band theory of metals was proposed by Bloch in the year 1928 in order to study how the metals they exhibit the properties which are related with the presence of electrons, such as the thermal conductivity, electrical conductivity, the metallic luster, then the tensile strength, magnetism, elasticity, sonority, all these properties which are depend upon the presence of electrons. How can we explain either of these properties by applying these theories that is to be studied? In this context, we have already completed the free electron theory or electron gas theory. According to band theory of metals, it is revealed that the basic condition is that the substance or the element which really acts as a metal should have an empty atomic orbital in its valence shell. In this regard, we have seen that lithium is a metal because it is having an empty 2p orbital. Similarly, those elements which behave as a non-metals, they are lacking in presence of the atomic orbitals in their valence shell. So those elements which behave as a non-metals, they do not contain empty atomic orbitals in the valence shells, and hence they are referred as a non-metals. In this regard, we have seen some two examples of carbon and nitrogen, where carbon is having electron configuration 1s2, 2s2 and 2p2. After excitation, one of the 2s electron is promoted to 2pz level. So it is carbon atom does not contain any empty atomic orbital in its valence shell. So there is a lack of empty atomic orbital in the valence shell of carbon. Hence, it is a non-metallic element or non-metal. The same is true for nitrogen also, which is having the 5 electrons in its valence shell. So, no empty atomic orbitals are present. Hence, nitrogen is also a non-metallic element. We have also seen that according to molecular orbital theory, the newly formed molecular orbitals, either bonding or non-bond or anti-bonding molecular orbitals, these are exactly equal to the participating atomic orbitals. Yesterday we have seen some 3 to 4 examples where we have considered that if two atomic orbitals are there, then two newly formed molecular orbitals are there, amongst which half will be bonding and half will be anti-bonding. Now, I would like to show you again the part that we have covered yesterday, which will be beneficial for the understanding part that we are going to study today. Now, just now I have mentioned that the metals are some elements which are referred as a metals because they contain empty atomic orbitals in the valence shell. For example, we have considered the example of lithium where 2p orbital is empty and hence 2p orbitals do not contain any electrons, hence this is a metal. The non-metallic elements which are lacking in the presence of the empty atomic orbitals, that means the valence shell of which are completely filled with electrons and hence they are lack of empty atomic orbitals in their valence shell and hence are referred as a non-metallic element. For example, carbon, just now I have mentioned that it is having the electron configuration 1s2, 2s2 and 2p2, one of this electron is unpaired and it is promoted to 2pz level. So no empty orbitals are there. So carbon is also a non-metallic element because of lack of empty orbitals. Similarly, we have seen the example of nitrogen also, where nitrogen contain 5 electrons in the valence shell, 2s2 and 2p3. So this also do not contain any empty atomic orbitals, hence it is a non-metallic element. We have also seen that the number of newly formed molecular orbitals are just equal to the number of participating atomic orbitals. If two atomic orbitals are there, two newly formed molecular orbitals are there, amongst which half will be bonding, that means one will be bonding and another will be anti-bonding. And if four atomic orbitals are there, four newly formed molecular orbitals will be there, amongst which half will be bonding. That means two molecular orbitals which are the bonding and two are anti-bonding, which I have shown here. We have seen this diagram also, that two atomic orbitals, they give rise to two molecular orbitals, one bonding, one molecular orbital which is having a comparatively low energy as compared to the participating atomic orbital, hence this is a bonding, and that orbital which is situated at high energy is known as an antibonding. So two newly formed molecular orbitals are there. Now if three atomic orbitals are there, three new molecular orbitals will be formed, amongst which one will be bonding, another is a non-bonding, and third is anti-bonding. If four atomic orbitals are there, four newly formed molecular orbitals are there, amongst which half will be bonding and half will be anti-bonding. That means two will be bonding and two are anti-bonding. If six atomic orbitals are participating, six newly formed molecular orbitals will be there, amongst which three are bonding and three are anti-bonding. This we have seen yesterday. Then we have also seen that if n number of atomic orbitals are there, then according to convention, n number of newly formed molecular orbitals should be there. So if n number of atomic orbitals are there, they give rise to n number of the molecular orbitals, amongst which again half will be bonding and half will be anti-bonding. So when these orbitals are formed, that is when these newly formed molecular orbitals are formed, there are n number of bonding molecular orbitals are there and n number of antibonding molecular orbitals are there. So they form a band of energy levels containing bonding as well as antibonding molecular orbital, and this band is known as molecular orbital energy band. So this band which contains half bonding and half antibonding, number of closely placed molecular orbitals are there, amongst which bonding and anti-bonding molecular orbitals will be there and they form a band of energy levels, hence it is known as a molecular orbital energy band. Now we have also studied that the 2s electrons of lithium, they do take part in mixing so as to form what is known as a lithium molecule, because lithium is having the 1s orbital which is deeply buried below 2s orbital, hence these electrons remain non-bonding, only 2s electron take part in mixing. So the bond that exists between two lithium atoms, this bond that is formed on account of the overlap of 2s atomic orbitals, which is shown here. So due to overlap or due to contribution of these two electrons, a sigma type of bond that exists between two lithium atoms. So this bond is of sigma, which is formed on account of the overlap of 2s atomic orbitals of the two atoms themselves. If we look at again the potential energy diagram, where we have considered only the 2s electronic subshell, where if two atomic orbitals are there, two newly formed molecular orbitals are there, and these are the two molecular orbitals which are shown, amongst which one is a bonding low energy, another is a anti-bonding high energy. So low energy bonding, high energy anti-bonding, and this distance corresponds to the internuclear distance, which corresponds to the bond length. So the bond length is nothing but it is the distance between the center of the two atoms of the nuclei. So this distance corresponds to the bond length or internuclear distance. Now we have seen one more concept in this regard, that is, if at all Li3 molecule is to be formed, then three lithium atoms they come closer with their 2s electrons and they form Li3. Here I have shown the valence shell electrons of the three lithium atoms. When they overlap, they give rise to three newly formed molecular orbitals, amongst which one is a bonding, second is a non-bonding, and third is an anti-bonding. The distribution of electron takes place like this. Now here the potential energy diagram for this formation of Li3 molecule, where three newly formed molecular orbitals will be there. One is a bonding, second is a non-bonding, and third is a anti-bonding. So this is how we have seen the formation of the three newly formed molecular orbitals as in case of Li3 molecule. Now, based on this concept, if we elaborate this particular concept for the formation of Li4 molecule, where four lithium atoms can contribute their 2s electrons, they give rise to four molecular orbitals, amongst which half will be bonding and half will be anti-bonding. So here, these are the four lithium atoms. They do contribute their 2s electrons for the formation of the two bonding and two anti-bonding molecular orbitals. Now, the energy profile for this we can show as like this, where we have shown that there is a formation of two bonding molecular orbitals, that is these two orbitals, which are lower in energy. So this is the average or mean energy, below which these molecular orbitals are known as a bonding, and above this average energy are known as anti-bonding molecular orbitals. So those molecular orbitals which is having high energy than the corresponding or average energy, these are known as anti-bonding, which are also two in number. Now today we are going to continue with the second part of this band theory, where we are considering if n number of lithium atoms are there, then they give rise to n number of molecular orbitals of lithium. How can we show this? Say for example, if n number of lithium atoms are there, then they give rise to the molecular orbitals like this. This is the mean or average energy, and if n number of lithium atoms are there, then n number of molecular orbitals will be produced. So here n number of bonding molecular orbitals will be there. The part that we show below this average or mean energy, this is known as the bonding molecular orbitals, and the part which is having high energy than the corresponding or participating atomic orbitals, this part we refer this as the anti-bonding molecular orbitals. So n number of anti-bonding and n number of bonding molecular orbitals will be there. Now, as can be seen from this diagram, the part that we have shown, which is labeled as a bonding molecular orbitals, which is filled by the electrons, or this band is known as the band which is occupied by electrons, which is known as a filled or occupied band. While this band do not possess any electrons, hence this band is known as the empty, or which is also known as the vacant band. So two bands of energy levels have been produced by contributing n number of atomic orbitals, which can produce n number of molecular orbitals, amongst which half will be, this is a half part, half will be bonding, that is n number of bonding, and n number of anti-bonding molecular orbitals are there. So two parts or two bands have been produced. So these are known as two bands, amongst which one band that is known as a filled with electrons or occupied with the electrons, that is known as a filled or occupied band, and this band is also known as valence band, and which is normally abbreviated as VB. So the band of electrons which is at a low energy known as a bonding molecular orbitals, this is according to band theory of metals is referred as a valence band, that is VB, and the band which is empty, which do not possess any electrons, this band is known as the conduction band according to the molecular orbital, which is normally represented abbreviated as a CB. So we can observe that there is a formation of two bands, one band which is a low energy, which is filled with electrons, known as a valence band, and another band which is at high energy, that is known, that is that do not contain any electron, which is vacant or empty with regard to electrons, hence this is known as the conduction band. So if we want to show the energy profile for n number of lithium atoms which are contributed and they can form the n number of molecular orbitals, then this is the increasing energy, this is the average energy. Here we can show the formation of the bonding and antibonding molecular orbitals. Here n number of bonding molecular orbitals are there. So here this part which is shaded part, this is known as the bonding molecular orbitals, which are n in number of molecular orbitals are there, and n number of anti-bonding molecular orbitals will be there, which are very large in number. So this particular distance, as we know, that corresponds to again the bond length as in observed in the formation of LIN molecule. Now, now listen very carefully regarding the better explanation for the formation of the valence band and the conduction band is that in LIN molecule, in LIN molecule, that is a formation of LIN molecule, which is on account of the AOs of LIN atoms, which can form LIN molecule. The molecular orbitals are more and more close in energy. So these are the molecular orbitals which are very close in energy, because n number of bonding molecular orbitals will be there, and it can be imagined that the difference between the energy levels of these various MOs will be very small. So if we consider a two molecular orbitals which are very close in energy, or the successive molecular orbitals which are very close in energy, there is no energy gap as such, they are very closely spaced. So the molecular orbitals very close in energy, so they lose their individual identity and they merge into a band. So this is known as the band of bonding molecular orbitals, called the molecular orbital energy band. This contains n number of bonding and n number of antibonding. So the n number of bonding molecular orbitals and n number of antibonding molecular orbitals, they form a band of molecular orbitals where the bonding and antibonding molecular orbitals are very closely spaced. This is known as a molecular orbital energy band. This contains n number of bonding and n number of antibonding molecular orbitals. So only the bonding molecular orbitals, they are filled with electrons, while the antibonding molecular orbitals, they remain vacant. Thus in lithium, only half of the molecular orbitals in 2s band are filled. So this is on account of the overlap of 2s band of n number of lithium atoms. So in lithium, only half molecular orbitals will be filled, while the anti-bonding molecular orbitals are vacant or empty. The lower 2s energy band is occupied by electrons and hence it is known as the valence band, which is abbreviated as a VB, while the upper energy band which is vacant or empty is known as the conduction band or CB. Now, in lithium, the valence band and the conduction band are present in the same 2s band. So this is a entirely 2s band which contains the valence band and the conduction band. The Now, the valence band which contains the electrons, because the energy levels are very closely spaced. So here n number of electrons will be there. So to promote one electron or one or more electrons from the bonding molecular orbital, that is valence band, to conduction band, very less amount of energy is required. Why? Because the anti-bonding and bonding molecular orbitals are very closely spaced. Hence, those electrons which are present, very less amount of energy is required to promote or to move the electron from the valence band to conduction band. So in doing so, they conduct either heat or electricity. So this is how the metals, they conduct heat or electricity. So on this basis, the electrical and thermal conductivity of metal can be explained. So this is how we can see the band theory of metals. So here, while studying or while explaining the band theory of metal, one should bear in mind that this is a very important part with regard to the band theory of metals. So if n number of lithium atoms are there, atomic orbitals are there, then n number of molecular orbitals will be there, amongst which half will be bonding and half will be anti-bonding. So when n number of lithium atomic orbitals, they combine, they form a band of the molecular orbitals which are very close in energy. So they lose their identity after the formation of the molecular orbitals. So while writing the explanation for the band theory of metals, you should write that if n number of lithium atoms are there, then n number of atomic or molecular orbitals will be produced. So here the lowermost band, that is known as the bonding molecular orbitals, where n number of molecular orbitals are very closely spaced, that is known as the filled or occupied band. So this word is very important. The formation of two bands, one band that is known as a filled or occupied band, this band is filled with electrons and hence it is known as a valence band, that is a VB. And another band of molecular orbitals, that is known as the antibonding molecular orbital, which is empty or vacant band, which is referred as the conduction band. So because the molecular orbitals, they lose their original identity. What is the meaning of this sentence? See this figure again. Here we can distinguish, see this diagram. Here we can distinguish, this is one bonding molecular orbital, this is another bonding molecular orbital. This is anti-bonding molecular orbital, this is anti-bonding molecular orbital, because very lesser number of atomic orbitals of lithium are involved. Hence we can distinguish that these are the one bonding and another bonding molecular orbital. But the case is not true in case of the n number of atomic orbitals when are involved, one cannot distinguish. So all the molecular orbitals, they merge into one another and they lose their original identity and they form a band of molecular orbital. So we can observe that there are two different bands. One is a lower band, another is a higher band of energy level, and this is known as a molecular orbital energy band. So they form a sort of band, and because the two bands, that is the valence band and the conduction band, are very close in energy, or there is no energy difference as such. So by supplying very less amount of energy, we can perturb, or we can move the electron from the valence band to conduction band. In doing so, these electrons can conduct electricity in moving from the valence band to conduction band. So this is the characteristic feature of this band theory of metals, which can definitely explain the why the metals are good conductors of heat and electricity. So this theory, you should remember that the theory that is known as the band theory of metals, which is abbreviated as molecular orbital theory, which is proposed by Bloch in the year 1928, so as to explain the significant properties of the metals which are associated. So this is how the two theories of metals that we have seen. Now, after some time, we are going to study the next part of this topic, that is the classification of the solids. So I'm going to conclude this meeting, and you have to again rejoin by clicking the same link after some time. So in the second part, we are going to study how the metals are classified into different parts, that is the metals, insulators and semiconductors, based on the band theory of metals. So we have to rejoin after few minutes. So we are going to study the classification of metals. So I am going to end up this meeting.